All right, 40 minutes after. Oh, can you hear me all right? All right, so today we're going to continue with our discussion about we started two-dimensional kinematics last time. We're going to continue with that today with lots of demos. So you can see that I'm telling the truth. We'll actually check and see that experiments agree with what I claim. Early drop deadline is this Friday. If you or someone you know is going to drop this class, I'm sad you're going to leave the class. I'd love it if you stay. But if you know you're going to drop the class, do it as soon as you can so people can get in the class. Because there are people waiting to get in here who need it. They're going to be in active probation. Their live streams will be ruined if they can't get in here. So make sure you drop soon if you're going to do it. I hope you don't drop though. I'll stay in class. All right, so today we're doing we're getting into chapter 3 stuff. Thursday we may get so far as chapter 4. Next week for sure we'll get into chapter 4. Okay, and mainly as I said today, we're going to focus on 2D kinematics. And we left off last time thinking about this problem over here, the shot and the drop balls. We actually did the demo. We saw that they hit the table at the same time. I'm going to show you both how to calculate it and how to think about it, like what's the intuition behind why that's true. And we're going to look at some more complicated examples of that sort of phenomenon and see if we can think through what's going on. The equations we've got, right? The main equations we're using at this stage in the class are just describing motion of objects. Oops, I got lots of props today. Gotta be careful. There we go. For example, we've got equations that define the acceleration and the velocity, and we have two sets of equations. We've got equations for the special case of constant acceleration, and we have general equations that are always true. It is always true, right? Here, I'll label them this way. Let's say always true. 2 L's? No, never 2 L's and always true. And then this is only for constant acceleration, right? What's always true? What's always true is that the velocity, I'm going to write it as a vector today, because we're getting into 2 dimensions, right? So the velocity is defined to be the derivative, let's use r instead of x. We're talking about a 2-dimensional vector. So r has 2 components, got x and y, dr dt, right? And we've got acceleration definition, that's just the derivative of the velocity with respect to time, and we know we can write that as a second derivative with respect to time of the position, right? Every one of these equations, well, there's 2, well, I guess we're going to call these separate equations. The equation for velocity and the equation for acceleration, each of these are actually pairs of equations, right? So it's really clear. This thing is just saying that the x component of the velocity equals dx dt, right? And the y component of the velocity is dy dt. This is just a compact notation to represent the same thing. So that's all we mean. Whenever you have an equation up here on your whether it's on a homework problem or on a test or whatever, for this equation to make any sense, the kind of beast that appears on the left had better be the same as on the right. In other words, this thing is a vector, this had better be a vector. And it is. There's 2 components here, 2 components here. In fact, we can write them out. V sub x is dx dt and so on for y, right? Anyway, so these are definitions. They're always true. It's also always true that the average velocity, I'll write it as a vector. So now I've got a bar for average, I've got a vector, an arrow for vector. That's equal to the change in the position, which is a vector, right, over the change in time. That's always true. We also have a definition for speed, right? Speed, we said, I'm not going to give a symbol for this, I'll just write it as speed. The speed is the length of the velocity vector. So in fact, this is the instantaneous speed. Although if we stuck in the average value for the velocity, well, actually, is that true? The average speed. Let's be careful about how we take our averages. To do the average speed, we have to be more careful than just taking the average of the average speed. But if we excuse me, the absolute value of the average speed. But if we want instantaneous, the instantaneous speed, we can do it this way. And what do I mean by that? Well, in 2 dimensions, I mean vx squared plus vy squared. Okay. So this is just definitions, and these things are always true. It doesn't matter what kind of motion we're talking about. If it's 2-dimensional motion, these equations are always true. Now, for constant acceleration, and I'll actually say, I'll put an arrow on top of that to indicate I mean constant in both the x and the y. Both the x and the y components of the acceleration are constant, whatever they are. Then we've got a bunch of other equations, right, that are more specific than these. The one that I think is most familiar, say, oh yeah, r equals r naught. The naught means time 0, right? No subscript here means the final time, but we don't bother to write it. I'm just using the book's notation. What is it? It's r naught plus, let's see, what is it? V times t. But which v do I want? I want the full vector v, and I want the initial velocity here, because the velocity is changing over time. If you have constant acceleration, it's not equal to 0. So this can be changing. The velocity itself changes with time, but v naught is a constant, just a number, right? So I stick that in, and then I multiply by t, and then I've got my 1/2 a t squared. Again, I need a vector sign. So that's true for constant acceleration. And we have some other expressions too. We know that the velocity. Here, I'll just put down the x components for the rest of them, just to mix it up a little bit. But it's true for the y components as well. We have v sub x. What's that? It's the initial value that it had plus however how much time has elapsed times the acceleration. Which acceleration? The acceleration component in the x direction, right? Anyway, so you guys know this. I'm just putting it all down so we have one board that's got all the equations on it. Today, we're mostly going to be using this equation, just because it happens to be the most useful for the particular problems I chose to demonstrate. But it's nice to know there's the others, and I'll just jot them down, that come up a lot. There's this one, x equals x naught plus 1/2 times the sum of the initial velocity in the x direction plus final velocity times t, right? And there's also this one has the velocity squared part in it, which is probably the most mysterious of these equations when you first see it, although it's not to be actually the easiest to understand when we get into talking about energy later in the semester. X naught squared, better be squared, have the units the same, plus 2 times a, and it's the x component of a, right? And x minus x naught. Oh yeah, and I want, yeah, that's right. Yeah, okay. So I think I got all my subscript right. And for every one of each of these equations, there's another set of 3 for the y direction, right? Great. So we're in 2 dimensions now. We did this problem last time. I'll just remind you. I think all of you saw it. I'll do it again. And the question to remember was, do they hit at the same time or not? Well, I'm already losing the ball bearing. Do they hit at the same time or not, right? And it turned out they did. Most of you voted correctly when I asked you, what do you think is going to happen? Most of you said, yeah, I expect they're going to hit the table at the same time. So, and those of you who did, have you seen, so who's seen this demo before I did it last time? Who's seen it before? Oh, a few of you have seen that before. I see. But that's great. All right. I think I'll do some demos today you have not seen before. So it'll be more fun to guess what's going to happen. All right. So as we saw last time, I'll go 1, 2, 3 and pull the trigger. 1, 2, 3, same time. Very good. Why is that? Well, there's an intuitive explanation, and then we can also just do it by the numbers and calculate it. What we did last time was we worked out just for the drop ball how much time it would take before it hit the table. So we said, question for the drop ball, what is the time at t hit, right? How long is it going to take to hit the table, right? And we said, all right, here's our situation. I'm going to draw, again, just like last time, I'm going to draw it backwards from your perspective, just so that way I can fit it on board and define my positive x-axis this way. I'm allowed to do that. The physics is the same whether I do it from this side or the other side, right? So I'll just make my life easy and choose my diagram just to make it convenient for me. I'll make this the y-axis. I'll make this the x-axis. For most of the problems we look at today, the convenient choice is going to have a horizontal and vertical pair of axes. But that's not always the case. If you have an incline in a problem, it often turns out that the smart choice is to have your axis at an angle, which is sort of disturbing when people first see it. Some students say, but I've always seen x-axis horizontal. It isn't always a convenient choice for axes. It'll make your problem simpler. It isn't that the physics equations will be wrong if you choose a different set of axes. It's just that it might be harder to solve the equations. They'll just be more algebra, just take longer, right? So when you choose your axes, you want to choose them so that you just make your problem as easy as it can be. And you have to do some work, but you can greatly diminish the amount of work you have to do to solve the problem if you make a smart choice of axes. So let's make this our origin, right? This is where x equals 0 and y equals 0. I just find the x-axis to be positive upward, So let's call this a positive number. And let's say we're told in the problem description that the height is d. So I'll say, okay, then this height right here is d. This is 0. Here's x. And the ball flies off like this. What else are we told? Well, for the shot ball, maybe we're told that the initial velocity of the ball is capital V, and it points exactly horizontally. In fact, that had to be true. When you all guessed or correctly told me that the balls were going to hit the table at the same time, you were working under the correct assumption that I had this thing lined up so that it comes out straight out to the side. In other words, if I had the spring angled up a little bit so the ball came shooting out at an angle a little bit upward, then which ball would hit the table first, the drop ball or the shot ball? The drop ball, because the shot ball had to go up in the air for a while, then come back down before it even got back to the same level it already was. Right? Whereas the other ball would have already been making some progress toward the table. That's right. And the opposite. Right? If I had it this way, I shot it down. Clearly, it would hit the table first before the guy who just was dropped would hit the table. But if it's actually starting off perfectly horizontally, which I didn't draw that as well as I could, make that horizontal, we'll give it a name, capital V. Now when I go and write my equations of motion, which we already did for the drop ball, let's do it again. You say, okay, we've got equations of motion for x and for y. Well, the x equation of motion for the drop ball is pretty boring, right? Because what is the initial velocity of the drop ball in the x direction? Let me write it out and see what we get. So what am I doing? I'm just writing out this equation just for the x component with subscripts of d, meaning dropped, for the drop ball. I'm just pedantically going through the problem. This is like a simple problem. You wouldn't necessarily have to go through this step, but I just want to make clear how we go through these things before we get to more complicated examples. So now I say, okay, it's the initial component of the drop ball in the x direction of the velocity. So I got 3 subscripts. Initial time, x component, d for the drop ball, times t, right? And then I got 1/2 times what? Times acceleration. But which acceleration? It's the drop ball's acceleration, and it's the x component of its acceleration, right? This is an equation that's just for the x component. And then I need t squared at the end. And so the question is then, how much of this can I get rid of with my choice of axes? Well, what is x of the drop ball at time 0? Oh, you might be bothered because I drew a little bit of a. Let's say that I went ahead and made a really smart choice of having this guy lined up perfectly with the axis. So I drew it. I see. There's some physical difference between these 2 points. What I would probably do in a problem like this is have different x and y axes for the 2 balls. Or in particular, I'd have a different x axis for the 2 balls. I would just simplify the problem and say, well, I'm going to assume that they both drop from the same x value, right? In other words, I'm going to choose. So here's what's given. I'm going to say that x naught for the drop ball equals x naught for the shot ball equals 0. I'm going to do that to make my life easy. It's not going to change anything if I had decided to actually have them on the same set of axes and with this difference actually indicated so that this guy is like half a meter or whatever this is, 10 centimeters to one side. Well, okay, it just complicates things in one way. The equation of motion is going to be that x equals negative 10 centimeters for all time instead of equal to 0. But I'm allowed to actually, I'm allowed to go ahead and just say that they both have the same x value to start with. It's not going to change the physics of the problem. So I'll go ahead and do that. I'll make my life easy and just say they both equal to 0. So I'd say, all right, that means this equals 0. What about the initial velocity, the component of velocity in the x direction? What is that for the drop ball? Yeah, it's 0. Lots of zeros. I love it. What is the acceleration in the x component to the acceleration for the drop ball? It's also 0 because the drop ball, just like the shot ball, only experiences acceleration straight down, right? In other words, gravity is the only thing acting on either of the balls once they're released from this object, right? And so all the acceleration is well, the acceleration only has a vertical component. It's pointing straight down. So this is 0. So after all this hullabaloo, the equation is that the drop ball's x value is always equal to 0 for all points in time. Unsurprising. Also for the drop ball, we can look at the y direction of motion, and we write down the same exact initial equation as the one we want. We used it last time. All right, yd equals yd naught plus v in the drop ball into the y component into the initial value of the y component. Lots of subscripts. All right, a dy t squared. Once again, let's see, what is the initial y value? The initial y value is actually positive d, right? But the final y value, what's that? That's right. If what I mean by t here is t hit, the time it hits the table. So I'll just put that up here to make my life simple. T equals t hit when it hits the table. Just don't have to put all the hit subscripts and all the t's, because all the t's in this problem are going to be the same. Right, that means this equals 0. So I got 0 equals d plus, oh yeah, and what's this? What is the initial component, the initial vertical component of the velocity for the drop ball? 0. Great. 0, 0. Good. So I only get this part. I get the 1/2. And what's the acceleration in the y direction of the drop ball? Yeah, it's 10 meters per second squared. Is it positive or negative, given the conventions I've chosen? It happens to be negative because I chose upwardly positive y-axis. So that means that I can put a plus here and then put minus g, because I'll define g to be a positive, right? My definition is, we did a lot of stuff here last time. We're basically moving to new stuff. So, all right. So given all that, I can just go ahead and stick the chase, put that there, and say, that's what I got. So again, that's what we did last time, and we were able to solve for t. What is t then? Well, d goes over here. They're both positive. It's d times 2 over g. 2d over g square root. Very good. So that's the same answer we got last time, right? Question? All right. Good. Units are good. Right? Meters, meters per second squared, second squared, seconds. Good. Time in seconds. Limits make sense. Bigger d means bigger time. Bigger strength of gravity means smaller time. It's so on, right? Positive answer, positive time. Very good. So what about for the shot ball? So if we do the same thing now for the shot ball, we get a more interesting equation in the x direction, right? What happens in the x direction? Well, now there is some motion in the x direction for the shot ball, but it's not that complicated because what is the acceleration? What is the x component of the acceleration for the shot ball? So the shot ball is flying out of the side, right? Once it's in the air, it experiences acceleration to gravity. Which way does that point? Straight down. There's no x component to the acceleration of the shot ball. So the equation of motion for the shot ball, I could go through the whole thing and write this whole thing out, but now it's got, instead of having d's, it's got s's everywhere for shot, right? And when the dust clears, what do I get? I find that the x value for the shot ball is just equal to the initial value, oh yeah, which is 0, right? 0, so I'll get rid of that, plus the initial value of the shot ball in the x direction, lots of subscripts, times t, plus 1/2, oh yeah, but this is 0. The acceleration of the shot, the horizontal component of the acceleration of the shot ball is 0. So this is the only surviving term on the right. For the drop ball, there was no surviving term, it's equal to 0 all the time. But now for the shot ball, there is a surviving term, and it grows linearly with time, which makes sense. Once the ball shoots out here, it continues to move to the right. And if we just ask what is the x value, what is the horizontal position, it changes linearly with time, right? Look, twice as long a time, it's gone twice as far. That's what we found. In fact, we didn't write this in terms of what we were given in the problem description. We were told, oh, the velocity, the speed of the ball is capital V, as it shot out initially, the shot ball, right? So that means I can just replace this thing with subscripts with the particular value or the symbol that we're given to describe the problem. And because it's a positive, because the way I drew my axes, this is all positive. So capital V is a positive number, and I say, oh good, the x position is increasing with time, and it's positive. That all makes sense. And I get the right units, right? I get velocity times the time, that's meters. Ah, good. Now, if we look at the y direction of motion, what do we find? For the shot ball, we find that that the final y value is equal to the initial y value. So shot initial plus, let's see. Well, we need to have the initial velocity in the y direction of the shot ball. What is the initial velocity of the shot ball in the y direction, the y component of the shot ball? So what is its initial velocity, right? It's pointing straight to the side. So when I say initial, I mean it's just instantaneous, right after the thing, right after the ball, it's right here. It's just left the spring. Gravity hasn't had much time to act, hasn't had any time to act yet. So what is the vertical component of the ball's velocity? 0. Does that make sense? So right after the ball gets shot out here, it's only moving in the horizontal direction. There's no vertical component to its velocity yet. That means this equals 0. That little 0 means time equals 0, right? No initial velocity. Now we have the 1/2 times at squared. But what a is this? It's the y component of the shot ball's velocity. What is that? What is the y component of the shot ball? Excuse me, acceleration. What is the y component of the shot ball's acceleration? No. What is it? Yeah, it's 10 meters per second squared. Is it positive or negative? Negative. So what we get is, and what is the final value equals 0 equals, so we're almost done with this, right? Because we're actually finding the same exact expression we had for the other ball. So we get 1/2 g times t squared. And so we arrive at the same exact equation we had for the y motion for the other ball. So that means that the times are the same, right? They're going to hit the table at the same time because they have exactly the same equations of motion in the y direction. They start at the same point. They have the same y component of their velocity initially. They have the same y component for their acceleration, and the distance they're traveling is the same. So everything's the same if we only look at the y direction. Now, if we look at the x direction, things are different, right? So if I ask you, so that answers our question. They hit at the same time. Okay. Same t hit for the two balls, right? As we found empirically by doing the demo. So what if I ask you a different question, like which ball is moving faster? Which has a greater speed when the balls hit the table? Do they have the same speed when they hit the table? Who thinks they have the same speed? Nobody. Who thinks they have different speed? All right. Yeah. And so which one's faster? The shot ball or the drop ball? The shot ball. And if I were to calculate how would I do it, I'd say, the speed of the shot ball, shot ball. That's just going to be the square root of, let's see, how do I calculate the speed? Well, I know how to calculate the speed. I can use this equation over here. V is the initial velocity plus at. In the vertical, I'll do that real quick. What is the final velocity of the shot ball in the y direction? Well, it's equal to the initial velocity of the shot ball in the y direction. That's equal to 0 because it started from rest, right? And you might say, wait, it didn't start from rest. That's true. The vertical component of the velocity was 0, though, which is what I care about for this equation, right? And then I add to this at. And the a I want is the y component of the shot ball. That's equal to negative 10 meters per second squared, right? Or negative g. And I got my t. And we already calculated t. So in this, again, when the dust settles, what I get negative g times square root of, what was it again? It was 2d over g. And the g's cancel out inside the square root, so I get a negative square root of 2gd. I think I did this last time. Anyway, negative velocity y because it defined upward to be the positive y direction. So that's why it's got a negative velocity at the end. It's traveling downward. Right? That makes sense. If I want to know what the speed is, I stick this in for the y component and say, okay, that squared, that's 2gd. And now I've got to add on, right? Remember, this is a different calculation here. Now I've got to add on the x component for the velocity. What is the velocity of the shot ball in the x direction when it hits the table? In terms of the symbols we're given in the original problem. Well, what's the initial velocity in the x direction of the shot ball? It was capital V, right? That was how fast it was moving to the right. Over time, there's no acceleration in the horizontal direction. So the horizontal component of the velocity of the shot ball isn't changing. So that means the final velocity, the horizontal component of the final velocity will be the same at the end as it was in the beginning. It's just equal to capital V. So I can stick in my capital V here, and I have to square it. So all I've done here, this is just Pythagorean theorem. Is there something wrong?
Your answer for the final velocity of the shot in the y direction is negative square root, so wouldn't it be the square root of negative square root 2gd?
It'd be the square of the negative square root. So I'm going fast and loose here. What I'm writing is this. That's a good question. So what I'm trying to do is I'm saying, it's the x component. Oh no, is that y or x? This is the y component squared plus the x component squared. I think that's what I'm doing here. Yeah, and it's the final values of the shot balls in both cases. So I know that capital V is the x component of the velocity of the shot ball at every moment in time, including when it hits the table. So I get V right there, and I square it. And the same thing here, as you pointed out, this thing is actually a negative number, right? We solved it. I got a negative number for that. But when I square it, the minus sign goes away. And that makes sense, right? If I'm using Pythagorean theorem, I'm trying to calculate. In other words, here's what I'm doing, right? The ball is actually coming down toward the table. As I drew my diagram, it's going down to the right. I know I did the demo the other way. But here's the final velocity of the shot ball, right? The total length of the velocity. And I'm breaking it up into two components. And I'm saying, here's the vertical component, v sub y, of the shot ball, and here's v sub x of the shot ball. And if I look at the direction of the arrow, right, this component is going down, this component is going to the right. Everyone see that? So breaking vectors into components is a major aspect of this class. And there are students who are pretty comfortable with a lot of the physics concepts, but it's very hard for them to keep their sign straight and keep their head straight when they break vectors up into components. So we're going to do this a couple times today. We're going to do it a lot next week, and I think Thursday. It comes up a lot. You'll do it a lot in your section on your homework and stuff as well. So the fact that this is down and I defined upward to be the positive y direction says that, the y component of the velocity is a negative number. But when I ask how long the velocity vector is, which is what we mean by speed, I take that value and square it and stick it in right here. So I always get a positive contribution to that part of the Pythagorean theorem, right? Even though this was a negative number. So I square this, I square that, add them together, take the square root, and I get a number that is